Welcome to my video lecture based on determination of single phase induction motor no load and block motor test. Myself Poonam Banerjee, Assistant Professor of Electrical Engineering Department, Dr. Sudhir Chandra Degree Engineering College. In every electrical machines, there are various tests are there to determine the parameters of induction motor, or it may be DC motor, it may be transformer, it may be synchronous machines. Any kind of machines are require different kinds of testings to know its parameters and its functionality, if it has some problem or its specification are correctly installed or not. Those things needed to justify our electrical machines will occur or operate properly. So here we will determine the equivalent circuit parameters of single phase induction motor using no load and block rotor test. In no load and block rotor test, basically it is performed on single phase induction motors based on two things. That is, first of all, it will be operated on no load condition, that means no loads will be connected with that motor, and second one, we will block the rotor of the induction motor mechanically and then we will do the test. So let us start with how this test can be performed and how these parameters can be measured. So the parameters of equivalent circuit of the induction motor can be determined from block motor and no load test. These tests are similar to those made on three-phase induction motor. However, except for capacitor and motor, these tests are performed with auxiliary winding fed token. For other types of single-phase induction motor, it is sufficient to perform the test with opening any of the terminals. So let us start with block rotor test. In this test, the rotor is at rest or blocked. A low voltage is applied to the stator so that the rated current flows in the main winding. You can ask me a question, what do you mean by rated current? Our aim, we have to flow the rated current through the machine. The rated current means, suppose this is a 1 kilowatt motor and our supply is 220 volt. Then our rated current will be 1000 divided by 220. That means 4.78 like that, 4 point something will be our rated current for performing that experiment. Okay, we have to remember that whenever we will do this test, we have to be concerned about the rated current. You have to be concerned that more than rated current should not flow through the windings. The voltage, current and power inputs are measured by using voltmeter, ammeter and wattmeter. Let VSC, ISC and PSC denoted the voltage, current and power respectively under this block rotor condition. That means short circuit voltage, short circuit current and power at short circuit condition. Block rotor means basically it is similar like short circuit condition of transformer. In case of motors experiment, three-phase induction motor or single-phase induction motor, we call it as block rotor. With rotor block, slip S equals to 1, the impedance Xn by 2 in the equivalent circuit is shown in the figure 8.6c is large compared with r2 dash by 2 plus jx2 dash by 2, that it may be neglected from the equivalent circuit. Therefore, the equivalent circuit of figure 8.6c at s equals to 1 reduces to that shown in figure 8.7a. Here 8.6, this figure we have shown in my previous lecture. From there you can compare this with no load test and block rotor test and equivalent circuit. Their parameters or diagram we have shown. The equivalent circuit referred to stator is now shown here. Now given this equivalent circuit, we can measure different parameters and that we will see in our next slide. Now from voltmeter and ammeter we have measured short circuit voltage and short circuit current. From there we can calculate the equivalent impedance referred to stator side, ZE. Now again we can calculate the equivalent resistance and that value will be R1M, which is main winding resistance, plus R2 dash by 2 plus R2 dash by 2. Ultimately we can calculate this equivalent resistance value by using P by ISC square, where P is the power output we have got from wattmeter reading and ISC short circuit current we have got the reading from ammeter. Since the resistance of the main winding is R1M is already measured, the effective rotor resistance at line frequency is given by R2 dash equals to RE minus R1M. So here we can again calculate the value of R2 dash by calculating P by ISC square minus R1M. Now from the figure we can again calculate the equivalent reactance value Xc, that is x1n plus x2 dash by 2 plus x2 dash by 2. That means ultimately the total equivalent reactance will be x1n plus x2 dash. Since the leakage reactance x1n and x2 dash cannot be separated out, we make a simplifying assumption that x1n equals to x2 dash. Now it will be x1n equals to x2 dash equals to 1 by 2 xe, that is half of root over jd square minus rt square. So we have calculated all the parameters referred to main winding, that is r2 dash, x1n and x2 dash, and all these parameters we have find from block rotor test when the main winding resistance value is known. Provided this value we have to know. Okay. Now we are going to no load test. The motor is run without load at voltage and rated frequency. In this case, we have to run the motor without load and at rated frequency and rated voltage. So we have to be careful that we will apply rated voltage and rated frequency and the motor should be at no load condition. The voltage, current and input power again similarly measured by taking a voltmeter, ammeter and wattmeter reading. At no load the slip is S is very small, close to 0, and R2 dash by 2S is very large compared to Xm by 2. The resistance R2 dash by 2 into 2 minus S, which is equals to R2 dash 2 into 2 minus 0, here slip equals to 0, so it becomes up to dash by 4. Associated with the backward rotating field is small compared to xn by 2. That the backward magnetizing current is negligible. Definitely in this case, backward magnetizing current will be very small, so we can neglect this value. And at that case, we are assuming that our slip value is 0 because at no load condition, the motor will run near about synchronous speed. That means our slip becomes almost equals to 0, so we are considering that this equals to 0. Therefore, under no load conditions, the equivalent circuit which we have shown in our previous lecture, we can refer to that. And from the equivalent circuit shown here, we can calculate the no load reactance x0 by using this x1n plus xn by 2 plus x2 dash by 2. Putting all those values, we can calculate the no load reactance. Since we know the values of x1n and x2 dash, which we have already determined from our previous block rotor test, so the magnetizing reactance can be calculated, Xn can be calculated from the equation given here. Now let V0, I0 and P0 are denoted by the no load voltage, no load current and no load power we have measured by using voltmeter, ammeter and wattmeter respectively. From here we can calculate the power factor cos phi at no load condition, that is P0 divided by V0 I0. Then we can calculate the no load equivalent impedance, that is Z0, which is V0 by I0. And again we can calculate the no load equivalent reactance, that is X0, which is equals to Z0 sin phi 0. Now Z0 into root over 1 minus cos square phi 0 is equals to the no load equivalent reactance X0. So we can calculate all these values from no load test. So from this test, block rotor test and no load test, we have all calculated all the parameters related to single phase induction motor equivalent circuit, and this test is very much important for knowing the performance of single phase induction motor. So this is a very important test and the motor should be tested before its operation, and this test can also determine the losses of induction motor. Here we can measure the core loss with frictional and windage loss included by using no load test, and copper loss can be measured by using block rotor test. So thank you all for listening my lecture.